So when we're talking about memory banking, we need to know that a memory is divided into banks so they can be accessed independently. And each bank shares address and data buses to minimize the pin cost. And in one cycle, one can start and complete one bank access. So and with this, a vector processor can sustain n parallel accesses if all n go to different banks. So this is a simple illustration of how the memory bank would look like. Let's say we have a memory of n banks, and then all banks share the same data bus and address bus. The MDR in here means the memory data register, and the MAR means the memory address register. So this way, the vector processor can handle this and parallel accesses at the same time if all the parallel accesses goes to different end. So, and this is how a vector memory system look like, where we have a base and we have a base and a stride and also an address generator. So as usual, we when we traverse through a loop, we usually start with the base address, with the base address and the stride, and we add them together as the address to access in the memory. Then moving on to the next address, the address the generator will use the previous address we used as the base, and then adds it with the stride, and then this will generate the next address, the next address to be accessed, and so on until the process is complete. So when we're talking about vector performance, we want to see how vector processor works efficiently and how is its performance compared to other processors such as the scalar processor. So to see how vector processor works efficiently, let's take a look at an example where we were given a problem to count for the average of two vectors containing 50 elements. And below you can see the scalar code we used to run the given loops, where the first line essentially assign an immediate to vector register 0, uh, to register 0, which is 50 as the immediate, and then the next three lines we assign the address of A, B, and C to register 1, register 2, and register 3 respectively. And let's assume that register 1, register 2, and register 3 will be incremented on every iteration of the loop. So when we use register 4 and register 5 to to store or to get the element or to load the element of A and B. And then we use register 6 to store the value or the result of register 4 plus register 5. And then register 7 is being used to store the result of the shift right once to simulate the division by 2. And we store the result back to the address pointed by register 3. And in the last line, we will decrement R0, which serves as the counter as to how many iterations should we go, and it will repeat the loop. Go in here, go back to X if R0 is still not 0. So beside the instructions, we can see their respective latency, where uh, for the move instructions, we need one cycle. And then for the load instructions, we need 11 cycles. For the add instructions, we need 4 cycles. For the ship, we need 1. For the store, we need 11. And then for the branching, we need 2. So assuming that we're doing this with only one bank, then we would get the first 4 cycle from the first 4 instructions, and the rest will be the 40 cycles, because the first 2 loads cannot be pipeline. So we will just take the 2 times the latency, and then we're just gonna get the sum of the cycles in one iteration, which is 4p, and then times it with 50 iteration, and thus we will get a 2004 iterations, or sorry, 2004 cycles. But however, when we're running it with 16 banks, then the first 2 loads can be pipeline, where we can reduce the execution time from uh, the whole execution time to 30 cycles instead. So by by the whole execution time, I mean the execution time of one iteration. So the first load in here, since it's pipeline, it will only take 1 cycle, and then the next load will take 12 cycle, and the rest will just be the same. And when we sum them up, this is 2. So this is the 1 and 11, so 12, and then plus 4 plus 1 plus 11 plus 2, then we will get 30. That's for one iteration, and then we multiply it by 50 for 50 iterations, and then also add for the first 4 instructions. So we'll get 1504 cycles. So looking at the loop, each iteration is actually independent of each other. Like for in the first element, there is no dependency between the first, the second, the third, and so on. So if that's the case, then we can vectorize this loop, because a loop is vectorizable if each iteration is independent of any other. So here we can see the vectorized code, and we're assuming that we're still using the 16 banks. So the first line will just be assigning 50 to the vector length register, and then the next one will be assigning 1 to the vector stripe register. And then the next is this line. We load the address A into vector register 0, which actually loads the whole 50 elements. And the same thing goes to vector B. I mean, when we're loading B to vector register 1. And then we do the vector add of register 0 and vector register 1, and store it in vector register 2. And then vector register 2 gets shifted once, and then the result will be stored in vector register 3. And then finally, we store the result of the value of vector register 3 back to the to the memory address C. Now, because the vector processor is already pipelined, for loading of memory address A to vector register 0, the first element takes, yes, 11 cycles, as what we have decided from before. The first for loading, it takes 11 cycles, and then the next element comes right at the 12 cycles, right? Since the first element takes 11 cycles, so the next element will come at the 12th cycle, and we basically sustain the one element per cycle. So it's basically just 11 for the first element, and then 1 cycle for the rest of the element. And this goes the same for loading vector B to vector register. For loading B into vector register 1, for the vector add, vector shift, and vector store, this will be the same, as the first element takes the full cycle, and the rest will just take 1 cycle per one element per cycle. So Let's assume that the following basic vector performance where we have no chaining at all. Then this means the output of a vector functional unit cannot be used as an input to the next vector functional unit. Or in other words, there's no data forwarding happening. And we only have one memory port with 16 banks word interleaved. So if we see the cycle below, the first two cycle are the assigning of length and stride, and then we load the memory address A, where the first element it will take 11 cycles. One loading of memory address A, the first element will take 11 cycle, and the rest will take 49 cycle, which is just one element per cycle. And the same goes when we're loading the memory address of B, and then when we're doing the add, the shift, and the store. So, and this will give us a total of 285 cycles in total, which is obviously better, right, than the 1504 cycles before. However, in vector processor, there's what we call the vector chaining, which is the data forwarding from one vector functional unit to another. So upon the first load from the memory, it load it until here, and then once the first element of V1 is ready, then it be chained or supplied immediately to the multiplier functional unit. And the same goes after it's done in here. When the first element is done, it will be supplied to the next functional unit, which is the adder functional unit. And this will be done continuously until we reach storing all the elements, or until we reach doing these operations for all the elements in the vector. So since going back to our question before, since our processor is still one port, we can't really parallelize the load of memory address A and memory address B. But so since we cannot load it, so once so we kind of need to load A completely first, and then but when we load the first element of B, we can already start the adder here, and then when we when the first element finish with the adder or the addition, we can immediately start with the shift here. However, we cannot immediately start with the store because remember that we only have one memory port. So at this at this time around the so at this time around in here, the load is still going on, so we kind of need to stall it for a bit. So the store will start after the load is done. So the total execution time of this of the vector code with chaining will be 182 cycles. Now, thus now we don't want the stall to happen, so let's try to change it up a bit and do a chaining with two load ports and one store port on each bank. So as usual, we should be able. I think with this one, we should be able to get a better execution time. So we can immediately pipeline the loads with the two load ports. So this is the first load, and then the second load, and then we can immediately start the add function once we get the first element of the B, and then we can immediately start the shift once we get the first element of the add, and I mean once the first element of the add is already ready for the next functional unit, and then we can start the store once the first element from the shift is done and ready to be used for the next functional unit. Then this way we can reduce this cycle to only 79 cycles. So from 1,504 cycles, we have reduced it to 79 cycles, which is around 19 times faster with the chaining and multiple ports to increase the performance of our vector code.